Hi, in this video I will talk about object detection with YOLO version 1. An object detection system outputs locations and types of objects in an image. Let's say we have a dataset of images and number of classes is 3. And this is an image from dataset. Class names are apple, lemon, and tomato. Object detection is to find location and class of each object of interest. A bounding box is drawn for each detected object. Bounding box indicates location, shape, and scale of the object. And class of each object is determined. YOLO version 1 is described in paper You Only Look Once, Unified Real-Time Object Detection. And the authors are Joseph Redman, Santosh Tiwala, Ross Girshik, and Ali Ferhadi. In YOLO, object detection is formulated as regression. Bounding boxes and class probabilities for all objects in the image are predicted in one single pass. Hence, its name is the abbreviation of You Only Look Once. YOLO is trained on full images and learns contextual information about classes. Features from whole image are used in detection of each object. Grid cells and bounding boxes. Input image is divided into S by S grid. In our example, S is 7. Each grid cell can detect only one object. If center of an object is inside the grid cell, that cell is responsible for detecting the object. Black dots indicate object centers, and highlighted grid cells are responsible for detection. Each grid cell predicts B bounding boxes and a confidence score for each bounding box. In our example, B is 2. Here are the bounding boxes for 3 responsible grid cells. For each bounding box, a vector of size 5 is predicted. Let's take one bounding box. And zoom in to see better. X and Y indicate bounding box center coordinates as offsets to grid cell origin. Top left corner. This is grid cell. And grid cell origin is at top left corner. X and Y are offsets from grid cell origin to object center. X and Y are normalized by grid cell size and they are in between 0 and 1. For this bounding box, X is 0.46 and Y is 0.33. W and H are width and height of bounding box. Bounding box width and height are normalized by image width and height, and they are in between 0 and 1. For this bounding box, width is 0.28 and height is 0.3. A confidence score is predicted for each bounding box. Model computes bounding box confidence score as an indicator of reliability of its predictions. Box confidence score provides the answers for two questions. How confident is the model when it predicts there is object inside the box? And how confident is the model about the precision of the bounding box around the object? In training, model learns to match predicted box confidence scores with ground truth box confidence scores. During training, ground truth bounding box confidence score is computed multiplying P of object with intersection over union. P of object is the probability that box contains an object. And intersection over union is computed between predicted and ground truth bounding boxes. In each training epoch for same input, predicted boxes change, intersection over union values change, so ground truth box confidence scores also change. In training, if a grid cell contains an object, the bounding box that has the highest intersection over union is assigned as responsible for detecting that object. This way, each bounding box adapts to detecting objects with certain sizes or aspect ratios. Ground truth confidence score computation. If grid cell does not contain an object, then P of object is 0 and confidence score is 0. If grid cell contains an object and bounding box is not responsible for detection, then P of object is 0 and confidence score is 0. If grid cell contains an object and bounding box is responsible for detection, which means this is the box with the highest intersection over union, then P of object is 1 and confidence score is equal to intersection over union between ground truth and predicted bounding boxes. For each grid cell, conditional class probabilities are predicted. If there are two bounding boxes for each grid cell and number of classes is n, then prediction vector for a grid cell is this vector. Confidence score, center coordinates, width and height are predicted for each bounding box, but conditional class probabilities are predicted for each cell. In YOLO version 1, each grid cell can detect only one object. P of C is the probability of class C given that grid cell contains an object. At inference, confidence score for class C is obtained by multiplying conditional class probability and box confidence predictions. Conditional class probability is multiplied with box confidence score, and result is class-specific confidence score, which indicates probability of class C inside the box and accuracy of the box. This is the prediction vector for just one grid cell. For a grid size of S by S, B bounding boxes in each grid cell, and n object classes, shape of network output is S by S by B times 5 plus n. To evaluate YOLO version 1 on Pascal VOC dataset, S is 7, B is 2, and n is 20. In this case, network output tensor has shape 7 by 7 by 30. YOLO version 1 network. YOLO version 1 has 24 convolutional layers. And 2 fully connected layers. One by one convolutions are used to decrease channel size. Sequential 3 by 3 convolutions provide larger receptive field. Input resolution is 448 by 448. Blue rectangles are intermediate tensors. Output size is 7 by 7 by 30 for Pascal VOC dataset. Linear activation is used after final fully connected layer. Leaky ReLU is used for other layers. YOLO version 1 Training. First 20 convolutional layers are pre-trained on ImageNet with input size of 224 by 224. An average pooling layer and a fully connected layer are added to these 20 convolutional layers for pre-training. After pre-training, average pooling layer and fully connected layer are discarded. Randomly initialized 4 convolutional and 2 fully connected layers are added to pre-trained 20 convolutional layers. Input resolution is increased to 448 by 448 and training continues with Pascal VOC. Loss function. This is the loss function used in the training of YOLO version 1. Sum of first and second terms is localization error. This term is related to box center predictions. And the second term is the error related to box width and height predictions. Model predicts square root of width and height. Square root is used to emphasize the errors for small boxes. Localization error is multiplied with 1 if bounding box J in grid cell I is responsible for object detection, otherwise it is multiplied with 0. Localization error is added to loss only for responsible boxes. Related lambda is set to 5 to increase the weight of localization error. Third and fourth terms are used to compute error related to confidence predictions. This term is used if box J in grid cell I is responsible for detection. In this case, ground truth confidence score is intersection over union between ground truth and predicted bounding boxes. And this term is used if box J in grid cell I is not responsible for detection. In this case, ground truth confidence score is 0. Number of bounding boxes responsible for detection is much lower compared to total number of boxes. To prevent model instability due to imbalance, related lambda is set to 0.5. Last term of loss function is classification error. This term is multiplied with 1 if grid cell I contains an object. Otherwise, it is multiplied with 0. Classification error is added to loss only if grid cell contains an object. That's why computed probabilities are conditional. Inference. At inference, network predicts confidence score, center coordinates, width, height for each bounding box, and conditional class probabilities for each grid cell. Model output can be visualized in two different ways. We can draw bounding boxes over the image. There are 98 boxes. Each bounding box has a confidence score. Also, we can create a probability map using conditional class probabilities. If there is an object in a cell, it is from the shown class with predicted probability. Multiplying box confidence with conditional class probability, we get class-specific confidence score for each box. Class-specific confidence scores are thresholded to eliminate boxes with low confidence. An object may be detected by more than one cell. Non-maximum suppression is performed for each class separately to discard duplicate detections. And class labels are printed. Limitations. Two bounding boxes and one class for each grid cell restrict the number of detections for close objects. YOLO version 1 has problems at detecting small objects, especially when they are close to each other. Since bounding boxes adapt to dimensions of objects in training data, YOLO version 1 has difficulty when it sees an object with different aspect ratio or scale. Coarse feature maps are used to predict bounding boxes, and this decreases detection performance, especially for small objects. Loss function handles width height errors similarly for small and large boxes. A small change in box dimension causes a larger change in intersection over union for a smaller box. In order to compensate for this up to some extent, square roots of width and height are used in loss computation. That's all for this video. See you next time.